Hello and welcome to our today's webinar about the application of CFD for the design of smoke control systems in a car park. Today we will introduce you into the world of cloud-based simulation and how that technology can help engineers and architects around the world to optimize smoke management and fire protection systems. It's nice that so many people have joined for today's session, and first of all I would like to introduce myself. My name is Milad. I've studied mechanical engineering at the University of Hanover, and in the past 10 years I worked as an engineering consultant in different industries like automotive and aerospace, and independent from which industry I was working in, I was dealing with simulation technology and how engineering simulation can help to design better products. And I'm working for 4 years now as a product marketing manager at SimScale. And as a part of my role here at SimScale, I'm organizing and hosting on a regular basis workshops and webinars which are introducing new users and interested engineers into the world of engineering simulation. In the case you have a question related to our today's webinar or something else, don't be shy and feel free to reach out to me using my email address mmarfi@simscale.com. Alright, so let's get started. And first of all, I would like to take a look at our today's agenda. So this session today actually consists of two main parts. At the beginning, we will talk about fluid flow simulation, also called CFD in general. You will learn how and why simulation can accelerate building design processes, and you will also learn which barriers limited the application of simulation in this industry in the past and how SimScale, or we at SimScale, want to deal with that. And after that, we will dive into the world of smoke management and talk about related aspects of simulation. Therefore, we have prepared a generic simulation project about the car park, and we have prepared simulation for that geometry, and we will show you how we actually use simulation to predict the smoke distribution inside the parking garage and how we can use the simulation results to later improve the design. Yes, we will also discuss the results of that simulation, and at the end we have a Q&A session where I will try to answer all of your questions. In the case you have a question, please feel free to submit it using the question window, which is inside the software we are using to deliver the live stream of that webinar. And you can just write it there, and I will try to answer on most of the questions directly on the fly or latest during our Q&A session at the end. Well, so let's get started. And first of all, let's talk a little bit about benefits of simulation and what simulation is in general. So first things first, and I've prepared a slide which you can see right now on your screen. And in the middle of the slide, you will see a picture showing the facade of a large building. And the story of this picture is actually a very good introduction into the world of simulation. So this image is showing the facade of the University Hospital in Aachen. It was designed and built during the late 60s in Aachen, which is a large university town in the west of Germany. And back then, when this hospital was planned, there was no simulation technology available for building projects. So this was really at the beginning of the journey of simulation. And back then, simulation was maybe used in aerospace or defense industry, but not at all for building design. And back then, they had to plan the full hospital, and one very important part for a hospital is actually the HVAC system. As you can imagine, it has a big impact on let's say the health of the patients. On the one hand, you want to have, let's say, thermal comfort for the patients, and on the other side, you also have some, let's say, harder requirements. For example, that you want a HVAC system which is limiting the pollution or the spread of bacteria and other things you don't want to be spread around the hospital. And however, they planned everything based on some rules of thumb they had and some tables and all the methods. And when the building was finished after some week, it came out that the HVAC system, the ducting system, was completely, let's say, underestimated for the big building, and that it was not able to really ensure a ventilation rate which is satisfying. And they tried everything, but in the end of the day, it came out that really the pipes of the HVAC system, the duct segment, was much too small, and there was simply no space anymore inside the building to put their larger ducts. So what they had to do in the end was that they've built up a completely new ducting system, which is like an exoskeleton outside at the facade, because it was the only area where they had space, and that's how it's looking now. It's super, let's say, ugly, but besides that, it's also very expensive, and we're not talking about building it, but also like maintaining it is much complexer, much more expensive, since everything is outside. And this is a perfect example. If they had simulation back then, simulation would give them the answer that this design is not satisfying, and it's really a good example for what is so unique about building projects, because at the beginning of such a project, you are actually defining the most of the costs which will, for the future. On the other side, usually at the beginning of such a project, only a couple of people are working on it, and decisions which are taken at the beginning of such design process can have a very big impact on, let's say, the outcome of such a project. And that is actually a perfect example which shows why design engineers, architects, and civil engineers should care about simulation, because it allows them to test scenarios and to understand the design at the very early design stage without building a prototype at all. And if we want to, we can also take the story and have a, let's say, more general look on it. So CFD, or in the end every kind of engineering simulation, is in the end a virtual laboratory. It allows us to test designs without having without the need of using a physical test facility like a wind tunnel or a test rig. You also don't need to build a model. So first of all, CFD allows you to test designs and judge about their efficiency without building a physical prototype. And this is super powerful, because if you think about it, whenever it comes to design a product, and independent if we're talking about a building, a ship, a car, or a plane, we have, let's say, different kind of design loops, and whenever we want to test such a design, what takes most of the time and money is actually building the prototype. And when it comes to buildings, for example, it's actually not even possible to really build a prototype. For some very specific applications, they do, for example, wind tunnel testing, but in general, for building projects, you only have one shot. And when something does not work, it becomes very expensive. And that's a great thing about simulation. It really reduces, first of all, your time investment, because you can, with, very little effort, you can test different design scenarios at the very beginning, and it saves a lot of time because you don't have to wait for a prototype to be manufactured or for a test rig to be available. It also reduces, let's say, the chance that something fails, because you're not testing it at the end of the design process, but at the very beginning, where you still can influence, let's say, the global direction of your design. And at the end, it helps you to save costs, because it not only reduces the time you need to develop a product, but at the same time you need less resources, less money to run that design process, or to run that simulation-based design process. And actually, these are the main reasons why engineering simulation, in particular CFD, so fluid flow simulation, can add a huge benefit to a building design project. And I mean, what I've told you now, it is very general. You can also apply these benefits, or they're also valid, let's say, if you want to use simulation to design an airplane. So let's try to understand what are the, let's say, benefits for the AEC industry or for building projects. And first of all, and that's what we will talk also about, it can help us to design, improve, and validate the performance of HVAC system and parts. Whenever it comes to smoke control, we use, let's say, techniques or other kind of building equipment to supply fresh air and remove the smoke. And we can use simulation, fluid flow simulation, not only to improve, for example, the design of a fan to increase the flow rate, or to increase the performance of a ducting system to decrease the pressure drop, but we can also use simulation to really understand how our HVAC system and its element are interacting with the room we want to ventilate. And this is very helpful whenever it comes to understand like what is the real world performance of a HVAC system. But besides that, we can also use a simulation for, let's say, more general things like improving energy efficiency. And I know when it comes to a fire scenario, usually you don't care so much about energy efficiency, but also, which is a part of smoke management, for example, is to make sure that daily pollutants like carbon monoxide in a parking garage are removed in the day-to-day operation. And there, whenever you have a system which is like running all the time, it can have a big impact on the overall energy efficiency of the building, and also some other things like LEED ratings, which you, for example, want to have for your building project. And their simulation really helps us to save money, because we can test different scenarios and find out if there is, for example, a situation or let's say a ventilation concept which we can use, which is more effective. And besides smoke protection, this is massively used whenever it comes to thermal comfort and natural ventilation, which can be optimized using CFD simulation. Another thing which is maybe not so important for smoke management, but which is very important when it comes to the facade design, is to predict wind loads for large buildings. There you can use CFD really to get an idea about the forces acting at your building. And whenever it comes to very large buildings or very tall buildings or very large bridges, methods we use for small buildings are not valid anymore. And there it's a really cheap alternative to wind tunnel testing, because not because only it's cheaper, but also because it provides us much more information than a wind tunnel test. And for sure, you can use it, as I mentioned, to optimize thermal comfort inside buildings, or also for the control of air quality and contamination, what we will do today in order to optimize the smoke removal inside the parking garage. All right, and now I would like to introduce you to SimScale, and I will make this section very crisp, but I mean, I told you so many positive things about simulation, and from what you've heard so far from me, you must think simulation is so great. Why is it not used by let's say, every engineer in the world? And actually, there are a lot of reasons why simulation today is only applied by a fraction of maybe 5% of engineers. And back then, 5 years ago, when we founded SimScale, we were frustrated by the fact that simulation can add or can help so many people, but it's only available to a minority of them. And we found out that there are actually 3 main, let's say, reasons or barrier why simulation is not a standard tool today. And in the very first reason was associated with the cost. Traditional simulation solutions or on-premise simulation software was very expensive. You needed to buy in advance like a 1, 2 or 3 year license, and just buying the license ended up like with the price of a mid-class car. In addition, you needed to buy very powerful computing hardware to run that simulations. Besides that, you also needed the right infrastructure, so you needed to hire people which are able to install the software, maintain your computing infrastructure, making all the stuff available to your engineers, and finally all the tools were designed for simulation experts and not for designers. And our idea back then was to make a platform which everybody can use to instantly create and run simulations without having the need to install anything, to buy any dedicated hardware, or to be an expert in order to use our software. And that is what we call SimScale. And SimScale is actually the world's first web and cloud-based simulation platform. And that means that SimScale is the first 3D simulation tool that you can access through your web browser. So you don't need to install any software. You don't need to have any dedicated hardware or any specific, let's say, computer, because all the computation is performed in the cloud, and you access the simulation tools through your web browser. So the only thing you need is a working standard web browser and a working internet connection, and you have actually the unlimited performance of simulation at your fingertips. And yeah, that new approach, this cloud-based simulation, comes with a lot of very interesting advantages. So first of all, SimScale is what we call an all-in-one tool. Usually when it comes to simulation software, you need to buy a license for the structural mechanics module. You need to buy a dedicated license if you want to do CFD. Sometimes you need to buy additional licenses if you want to use dedicated models or several processors at the same time to accelerate the computing time. And with SimScale, you can forget this, because all the simulations you can be set it up using the same user interface, and there is no difference regarding the license. You can access all the tools and all the solvers. The next thing is that due to the cloud-based technology, SimScale is super fast and easy. You are not limited anymore to any device. You can access your simulation project and data from everywhere you want, from every computer you want. You just need a working internet connection. And that's maybe the most important things, you don't need to think anymore about the, let's say, computational effort of your simulation, because it's calculated on the cloud, and through the cloud we will use as many computational resources as necessary to solve your problem in the time you need it. And this cloud-based approach is not only making the access to the technology easier and faster, but it also impacts, let's say, other areas of our product, like the support. Based on our cloud approach, you can reach out to our support team through different channels. We have an integrated chat in SimScale. You can directly chat with our engineers. You can also call our engineers by phone, and for sure we offer email support. Besides that, we offer consultancy, free webinars, and training. And everything is tailored to the platform. So you never have to think about like, oh, how can I adapt this to my model? Like, it's super straightforward. SimScale is also very cost efficient, and actually SimScale is starting for free. So you can use our free community plan where you have exactly access to all the features. Also our commercial plans have. The only difference is that a simulation project will be public. Based on your needs, you can actually scale how much you want to pay and get out of simulation. Yes, the cloud-based approach also makes collaboration very easy. So we have a community with more than 100,000 users. You can exchange with that users, share projects, find inspiration in our huge public project library, where you can import ready-to-use simulation project with just one click. And in the end, one thing which I really like, a lot of people think whenever it comes to cloud, it's about something which is not very secure. And actually, we think it's exactly the other way around. At SimScale, we have a large security team where experts are improving on a day-to-day basis technologies we use to encrypt the data of our users. Actually, our data is encrypted 2 times using AES, and we are not only encrypting your user data, but also your simulation projects. And you are the only one who have control about your simulation projects and who can access your simulation results. All right, now we talked, or I talked a little bit about CFD in general and also about our cloud-based platform. And this was quite general. So now let's try to link what we've learned in the last 15 minutes to smoke management. And therefore, I would like to share some very general thought with you about how we can apply fluid flow simulation for the design of smoke control systems, for example, in car parks. Yes, and first of all, let's try to get a general understanding about the problem we're dealing with. So on the left side of the slide, you can see like the geometry of our parking garage. So we have like, we will discuss about the geometry in detail in some minutes. And actually we can use now CFD simulation to predict how the smoke will propagate through this space depending on the configuration of our HVAC system. And on the right side now you can see for another car park the simulation results. So here we have a slice like half a meter about the ground, 1 meter about the ground, which is representing the actual flow velocity. And you can see like these jets of the HVAC inlets and also like how the air is moving through the space and removed here, for example. And actually when it comes to smoke management, there are, or to the example of a parking garage, there are two things that we can investigate using CFD. First of all, what I called before day-to-day pollution, for example, of carbon monoxide of the parking cars, of the cars driving through the garage, which is our day-to-day scenario. And we also have the emergency scenario where smoke needs to be removed safely and fast through the ventilation. And both of these scenarios can be simulated using CFD. And then we can use the results also for some other, let's say, aspects of engineering. For example, whenever it comes to smoke protection and whenever we are planning scenarios of a fire, one very important aspect is to plan proper escape routes which clear and allow firefighting crew to easily access the fire. And there, for example, we can use the CFD results also with other softwares to find the optimal escape path in the case of fire for different fire scenarios. And also what we can simulate is where toxic gases are hazardous for occupants and in which regions, for example, the risk is very high and that people can get injured through a high concentration of these toxic gases. And yes, now in the next 10 minutes I want to show you a project we've prepared of a park car where we simulate a fire scenario. And before we take a look at that, let's just sum up how design of smoke control systems can be impacted by CFD. First of all, we really can design better solution. So we can do what we call performance-based design. Usually in the building industry, since they historically had the problem that there was not really the opportunity of testing, a lot of, let's say, design methodologies are prescriptive. So they're not really based on the actual physics we could measure at our problem, but they are based, let's say, on, yeah, you know, on old studies, on old knowledge, on experience. And this performance-based design really allows us not only to design this parking garage by following a standard or some recommendations from a fire protection agency, but by really comparing the performance of different designs using metrics you define or using like numbers, which is really enabling designers to go completely new paths and massively improve performance and energy efficiency of smoke removal solutions. It also allows us to really test virtually completely different scenarios and approaches to, for example, gain confidence. I mean, to be honest, I've never worked myself as a fire protection engineer, but in the end of the day, it's the same in every industry. You usually have something in your mind, the kind of direction or let's say way you would go based on the experience. A lot of times, especially at the beginning of such a project, you maybe have some completely new ideas how you could tackle the problem. And usually you don't follow them because the risk is much too high that it fails. And on the other side, you already have a solution which is somehow working. And here using simulation gives you much more confidence and time to really test new things at the beginning. And it's not only helping you to design better, but also faster, because you can, with our cloud-based simulation, you can actually run as many simulations as you want in parallel. So let's say you have 5 fundamental different scenarios. You don't need to wait for every scenario to be tested. You can test them all in parallel in the cloud. And I think what is for most of you maybe the most important aspect is that simulation helps you design more cost effectively, so design actually cheaper. You will avoid any over-designing or spending too much time or resources or energy on unnecessary component. And as I mentioned several times, it will help you to replace expensive experimental and investigations. Well, we have the first question by Mario, and Mario wants to know what toxic gases do we simulate and did we account for increased ambient temperature and what's about transient cases. So Mario, there are a lot of questions, so let me try to answer them. So first of all, in theory, we can actually simulate, let's say, every kind of toxic gas. It just depends on which model, or let's say it's suited to tackle that problem. So for toxic gases, we have different methodologies, and they are treated as passive scalars. So we are not simulating right now any chemical reactions, but how they will be transported through diffusion and convection within the flow field. And for sure, we can also account temperature. So we can also fully couple it. That means that we really calculate the temperature field for the whole simulation, so that we really have, let's say, buoyancy included in the simulation. But for a lot of cases, this is even not necessary, and there are easier methodologies, so easier models and ways to account the effect of increased ambient temperature due to a fire. And for sure, Mario, you can choose if you want to simulate a transient or a steady state case. This is just basically a user's decision. And a lot of cases, by the way, a steady state result actually gives you the same kind of information like a transient simulation. And just in, let's say, very special cases, it's really necessary to simulate it in transient, which for sure takes much more time and computational resources. All right, but I think a lot of this question will become clear if we take a look at the example. So this is the example I've prepared for you, and this is the geometry of our parking garage. So the CAD model of this parking garage is representing, let's say, the inner space or the inner volume, which is enclosed by the walls. And as you can see, we have, first of all, a lot of like pillars here, which stabilizing the whole garage, and then we have this different, let's say, parking lots. And at some points, first of all, we are like bringing in fresh air into our parking garage. And this is not only necessary in the case of fire, it's also necessary in the day-to-day operation, but for sure, usually when you have fire, you use a different ventilation strategy and different flow rates than in the day-to-day use. So we are supplying fresh air here and here. Here we have one inlet, and here we have 3 inlet, and each of them is supplying 80,000 cubic meters fresh air per hour. At the same time, we have exhaust openings here, here, and here, which are removing 3 times 28,800 cubic meters per hour. And we have a ramp, which is like the connection to the environment. So the drivers are using this ramp to drive in or out of the garage. And if you just take a look at this volume rate, it's obvious that we are like removing more air than we are like bringing in through the fresh air supplies. So this ramp will also work as a kind of inlet, since we have the conservation of mass inside such a system. And for simulating the fire, we have this, we will put here a smoke production location. So we will use the 2 meter multiplied with 5 meter volumetrical scalar source, where we will release momentum, which represents the temperature or the energy which is released by the fire, and also the pollutions with the passive scalar. And actually we have 2 design challenges. First of all, we want to make sure that we have acceptable smoke concentration levels inside this garage, so that we still have like clean paths which can be used as escape paths, since the concentration level is low in that areas. And also we could use the simulation results to optimize the jet fan sizing and placement, because usually you have what we call jet fans inside such a garage. This image is showing like how this is looking like. So this is like a tube with a fan inside, and they help to, let's say, steer the flow inside this garage into the right direction, and to, let's say, bring the smoke in the near of the exhaust. Well, and now let's switch to the SimScale platform. And everything I'm doing right now, I'm doing it in my web browser. So it's on simscale.com. You can also just go on directly on simscale.com. I don't need to log in. You could log in here, but I already have logged in. So let's switch to the dashboard. And here you can see all the projects I've set it up. And they're including a lot of different things. And now let's open this smoke control in a car park project. And now let's just open the project. And so we have uploaded 2 different geometries. The height of floor. We have really one geometry where we just have the parking garage, and we have a geometry where we've also added the jet fans I was talking about before. You can see them here. And the first thing you need to do is a step we call meshing. And meshing is the process where your continuous CAD model, your continuous domain of your CAD model, is transformed into a discrete model, which means we are like dividing our model into small sub-models of solid cells. And in the end of the day, later the computer is calculating pressure, velocity, and temperature values only for the center of each cell. And this step enables us to solve these continuous equations with the help of numerics with the computer. And yeah, so you can, I don't want to go too much into detail, but you can like choose between different mesh operations we have. We have full automatic mesh operations and half automatic ones, and then you can define different refinements, because let's say the resolution of the cells in the end of the day, it's representing the local resolution of your simulation. So as fine as the cells are, as more precise as your simulation in that area. And therefore you make the mesh, for example, smaller in the near of obstruction objects and far away from the flow, or in the near of the wall you make it also a little bit finer to resolve wall effects. And after you've set up the mesh, you can directly define the simulation by choosing what you want to simulate, in our case passive scalar transport. Yeah, and once this is done, you like just follow this tree. You define a domain, so which mesh you want to use. You can choose which is the fluid you want to simulate. In our case it's air. You can directly import the material properties from our material library, and then you define different like boundary conditions. For example, inlets, you can see the visualization here. And there we defined a volumetric inlet flow rate of 15 cubic meters per second. We also made the same for the exhaust. There we defined a negative volume flow rate. And we have one boundary condition for the pressure inlet of the ramp. And the fire source was brought into the simulation by creating a momentum zone and a passive scalar zone. So the passive scalar is introducing the scalar which we use to predict the smoke density, and the momentum source is used or is necessary to account also thermal effects and the buoyancy of the fire. And for example, let me quickly try to visualize that. For example, this here. And so here you can see like the volume zones where we define the fire. Yeah, and then you just need to decide like how many processors you want to use. In our case, 96 processors, so a huge computing power. And then running this whole simulation took 809 minutes, which is, yeah, you know, like 12, 13 hours. And don't forget, we used 96 processors. If you would do this on your standard CAD workstation, it would take you days to months. And here it took less than 12 hours. And then you can also visualize the simulation results directly in your web browser. Just click on solution fields. And by the way, this can sometimes take up to 10-15 seconds since you're really loading huge amount of data. In this case, millions of values for velocity and pressure of the flow field. And once it's there, you can like easily, for example, create a cutting plane, let's say in that direction. And let's say we want to visualize the concentration of the smoke, which is called T1. And then let's flip it. And this is our source, and now like we can move this slice and check what happens inside the flow field. But that's not only the only thing we can do. For example, we can even create trace particle and do a lot of other stuff. Well, and now I've prepared some of the results from that simulations and created screenshots just to show you quickly like which very valuable insights the simulation will provide us with. So first of all, let's take at the airflow pattern. Therefore, we will visualize the velocity flow field, which is a distance of approximately 1 meter from the ground. And like here you can see how air is introduced into our garage, how it's removed at some points, and blue means a very low velocity compared to 0, and red is a high velocity of 4 meters per second. And with initial design you can see that we have some mixing, but especially in this area here, let me see if I have a pointer here, we have a lot of blue areas where we have recirculation of flow, and the same thing here and here. And if we know for design 1, visualize instead of the velocity, the smoke concentration, we can see that we have a high, let's say really a high smoke density region here. And know where it's so black, you can't even see your hand before your hand. So such a big concentration is in this area. So there's definitely something we need to do about it. And what we did is for design number 2 that we've added this fans. And here you can see how this fans, they're not bringing any new air inside the system, but they are like promoting the mix of the air inside the space. And you can see like the big impact it has on the flow pattern. So especially in this area where we had the high smoke concentration, we added 2 of these fans. And here we can, with help of this visualization, we can really see how the fans are working and how the jets of the fans is interacting with the jets at some other points of the garage. And if we now visualize the smoke concentration, we have just a very small area with a higher concentration, which is, by the way, also lower than the peak concentration of design 1, which is directly in the near of the fire. But if we compare it, it's really a big change. And actually, we reduced the smoke concentration by more than 50%. Not if we just take a look at the peak, and if we take a look at the average concentration, it's even much more than 50% just by adding this jet fans. Yeah, and this small design change helped us to reduce the maximum smoke concentration by 40%. And in practice, this means that all the standards or the national building codes are, in the end of the day, defining a time frame in which the smoke concentration needs to stay under a defined threshold. And the next step, you could use the simulation to remove the number of fans you need and really to optimize the smoke scenario that it really matches with the requirements from your national building authority. Yes, and if you now get curious and want to get started yourself, there are just 3 steps you need to follow. First of all, you need to upload your own CAD model. Sometimes it's necessary to prepare these models for the step meshing, which I showed you, so you need to make sure mainly it's watertight and closed. Then you can set up the whole simulation in your web browser and do the post-processing and the design decision based on the result evaluation, which can also be performed in the web browser. All right, so that was everything from my side, and now we have time for your questions. So if there's anything you're not sure about, just put it into the chat window or into the question box, and I will try to answer it. So the first question is by Alberto, and he asks, smoke production depends on the geometry of the source and the flame. In order to correctly define the fire source, you should define either the reaction or a flame volumetric area, variable in time, with the source of heat and smoke product. Is this possible? Yes, Alberto. As I mentioned, we have different opportunities to model a fire. For this demo, we choose a simpler one to make it accessible to let's say, big part of the audience, but we also are able to let's say, incorporate more details, and some of the things you've discussed, like the fire source or the reaction, can also be added using a different methodology. And if you're interested in that, please reach out to me by email, describe me which kind of problem you want to simulate, and I can exactly tell you like which models are available for the flame. And if you're interested in that, you should take a look at our FDS sneak preview webinar, which you will find on our website, where we showed an example where we used the FDS solver with the SimScale platform. All right, it seems like all questions are answered. In the case you just get a question in the next couple of days, you can reach out to me using email. Yeah, I would like to thank you very much for being here with me. It was a great pleasure for me and a big honor to be your today's host. Thank you very much. And yes, I will send you an email with this project and some more information in the next couple of days. Have a nice day. Bye.